Assalamualaikum and hello everyone. My name is Muhammad Lokman Hakim bin Muhammad Noor and we are from class 2 BEEY S1/1 and my lecturer name is Puan Rozilawati binti Muhammad Noor and we gonna talk about Athena Asimov position control with fuzzy logic and self-turning fuzzy logic controller. So this is the list of our group members. Starting from the first one is Muhammad Lokman Hakim bin Muhammad Noor. The second one is Faiz Aidil bin Abu Hanifah. The third one is Wan Muhammad Syamil bin Wan Musa. And the last is Muhammad Johan bin Muhammad Zamri. Assalamualaikum and hello everyone. From this slide, I want to introduce about antenna azimuth position control with fuzzy logic and self-turning fuzzy logic controller. The first introduction about antenna azimuth position control with fuzzy logic and self-turning fuzzy logic controller is fuzzy logic and self-turning fuzzy logic controller can adjust the antenna's orientation in real time. The second one is input signals such as change in the environment or user command can be used to make this adjustment. Okay, for the next, this adjustment help to improve the accuracy and stability of the antenna position control, and it can improve the position control is critical for reliable communication and data transmission. Okay, when we talk about the application, control system with high accuracy and precise positioning have become increased important in the industrial and communication sector due to advancement in satellite and radar system. Currently, there is a system for managing the horizontal rotation of an antenna, which used to control techniques like fuzzy logic and PID controller. In this study, a self-adjusting fuzzy logic controller implemented in MATLAB or Simulink is used to control the positioning or location of the antenna in the azimuth coordinate system. To control the antenna, the angle is manually adjusted using a potentiometer while entering the desired position or location. For performance evaluation, the second potentiometer provides feedbacks. The rotation in the antenna to the desired angle is achieved by the DC servo motor with armature control system connected to the antenna via the gear mechanism. Okay, where the control is being used. The system for controlling the azimuth position of an antenna include a pair of potentiometer, one for the input and other for the feedbacks. The system also have preamplifier, a power amplifier, a DC motor driven by the armature, and the antenna. A parabolic dish antenna placement system is used to automatically direct to the antenna to the intended targets. This is the block diagram of antenna azimuth position control system. The system receives its input from the reference signal, which stands for the intended azimuth angle for the antenna. The antenna needs to be tracking the target position. Feedback is used to indicate the antenna true azimuth position, which is then compared to the reference signal to provide an error signal. When the reference signal and the feedback signal are compared, the error signal appears. It shows the difference between the antenna actual location and its desired position. For the fuzzy logic controller, receive the error signal and input and generate a control signal using fuzzy logic. It makes sure of the fuzzy rule and logistic variable to capture and use expert knowledge for precise control. The control signals of the output of the system is represented by the control signal which is produced by the fuzzy logic controller. It is a signal according with the error signal and the controller choice, control the movement and positioning of the antenna. The output of the control signal, which instruct the antenna to change its azimuth position, is the system output to reduce the error between the desired location and the actual position. The antenna moves in according with the control signal.
Assalamualaikum. My name is Faiz Aidil Livin Abanipah. I will talk about system model to get transfer function. This is our closed loop. First, we go to the input signal, and then it will go to the input potentiometer, and then it go to preamplifier, which is our gain 1, and then our power amplifier, which is our transfer function 1, and then it will go to motor and load, which is our transfer function 2, and then go to the gear. And after that, we'll go to the output, or it will go to our feedback, which is our output potentiometer, and then it will go to the preamplifier back. Calculation to get the peak time, TP, settling time, TS, and percentage of overshoot, which is OS, from the transfer function. From the transfer function 1, which is 100 over S plus 100, the peak time is 0.3145, the settling time is 8, and the percentage of overshoot is 92%. For our transfer function 2, which is 0.2083 over S plus 1.71, the peak time is 2.808, the settling time is 1.99, and our percentage of overshoot is 68.24%.
Okay, Assalamualaikum warahmatullahi wabarakatuh. This is the output graph for the system response of antenna azimuth position control. So we get here the TP is 2.5, and the TS we get here 2.36. Okay, this is the difference between calculation value and the simulating value. So we can see here that for TP calculation, we get 0.3145, and also we get 2.808. And for the simulating value, we get 2.5. And for the TS, for the calculation value, we get 8, and also we get 1.99, and also from the simulating value we get 2.36. So for the percent of overshoot, we get 92%, and also 68.24%.
Hi, my name is Muhammad Johan bin Muhammad Zamli. My matrix number is B0821104001. So, I will present my part, which is convert the system transfer function to state space representation. So, the formula is G equal to K over S power of 3 plus 101.7 S power of 2 plus 171 S. So as we see, the table, the calculation in the table, we get the matrix number, which is 11710 101.700 17100, and lastly 000. The system is stable because all the roots of the characteristic equation have negative real position, which is indicated by the absence of sign changes in the first column of the root table. Then we can get the value of K, which is 173.91. Thank you. Okay, for the next part is I will explain the stability of the system. In this subsection, we are examining the stability of the closed-loop system. If the calculated pole values indicate stability, then the system is stable. As a result, the value of poles we get are S1 equal to 0, S2 equal negative 99.98, S3 equal to negative 1.71. The system is stable because its poles are negative. Additionally, the system type is 1 since there is only one pole located at the origin. The calculation below at part J can prove the steady-state error of system. The calculation of part J based on our report. Thank you. So I will continue about calculate the steady-state error for step input, ramp input, and parabolic input. The transfer function is same as just now, which is G equal to K over S power of 3 plus 101.7 S power of 2 plus 171 S. So for the step input, I will skip the part calculation and I will explain about the final answer is. The final answer for step input, hence ESS equal 1 over 1 plus Kp, which is 1 over 1 plus infinity, we get 0. And for the ramp input, hence ESS equal 1 over Kv, same as 1 over 1.02, and we get the final answer is 1. And for the lastly, for the parabolic input, ESS equal to 1 over Ka, which means which is equal to 1 over 0, we get the infinity. So the steady state error is type 1, equal to 0, 1 and infinity. That's all for calculate the steady state error for step input, ramp input, and parabolic input. Thank you.
Okay, for discussion, from the graph, we can clearly see that the system is stable. The value of pole we get also negative in value, which means it lie on left side of graph. Hence, it's proven that the system is in stable condition. For the steady state error, we know that it is system type 1, as there is only one pole at origin. Antenna azimuth position control using fuzzy logic and self-tuning fuzzy logic controller offer a robust and adaptive approach to address uncertainty in control system. Fuzzy logic controller leverage logistic variable and fuzzy set to capture aspect knowledge and handle precise information effectively. Self-tuning fuzzy logic controller enhances this approach by automatically adjusting the parameter based on the system dynamic, ensuring optimal performance in real time. This combination enables precise tracking and stabilization of antennas even in the precise on charging environmental condition and disturbance.
In conclusion, the study of antenna azimuth position control with fuzzy logic and self-turning fuzzy logic controllers illustrate the effectiveness of fuzzy logic and self-turning fuzzy logic controllers in achieving precise control of antenna azimuth positions. The application of these intelligence control techniques enable the modeling and regulation of indicate and nonlinear system, providing flexibility in handling uncertainties and imprecise data. The self-turning feature further enhances performance by adapting to changes in system dynamics, ensuring optimal control in dynamic environments. Through experimentation and simulation, the research confirmed the superiority of fuzzy logic and self-turning fuzzy logic controllers in terms of tracking performance, error reductions, and robustness. These findings underscore the potential of these intelligent control strategies in enhancing the accuracy, dependability, and adaptability of antenna system. The study offers valuable insight for future advancement in antenna control through the utilization of physiologic and self-turning technique.